Another technique for getting more interesting shapes out of our Voronoi fracture is clustering. So with this technique, we can combine a bunch of our Voronoi pieces into one chunk. For example, we could perhaps combine all of these pieces into one larger piece to create shapes that are more interesting than any single Voronoi shape would provide. Now, the traditional way to do this was to add a cluster attribute to our input points. Right now we only have 20 points in here. Let's increase this to something like 4,000 for this demo so that we can really see the shapes represented well in our point cloud. And then let's create a point VOP to apply that cluster attribute. We'll be using lots of VOPs and wrangle nodes, and the same task can often be accomplished in either a VOP or a wrangle. But when working with noises, I usually like to work in VOPs. In VOPs, it's really easy for us to create a few different types of noise. You can create, anti-aliased noise. You can create a unified noise. And in this case, we're going to create a Voronoi noise. The interesting thing about the Voronoi noise is that instead of these sort of fluidly changing values throughout space, the Voronoi noise is going to operate similarly to the shapes that we get out of a Voronoi fracture. That is, it will create cells of values and give us a different integer value for each one of these cells. This will be more obvious when we visualize the noise with some color. So we've created a Voronoi noise node here, and we'll connect our input position P and to the sample position of the Voronoi noise. And to create a new attribute from that output, let's use a bind export. And on the bind export, let's set the name to cluster. And we're going to use the seed output from Voronoi noise as the input for that cluster. And now this seed, if you look at the bottom of our network editor here, when you hover over that, it tells you it's outputting an integer. And on this cluster export, even though the type defaults to float, this checkbox override type with input means that it will export whatever it's receiving. So you've got this noisy integer being exported to that cluster attribute, but we don't really see anything different in our viewport. So let's visualize that attribute to see what it really looks like. And of course, whenever we're working in Houdini, it's always good to keep your scene clean and rename everything as you go, especially when it comes to VOPs and wrangle nodes, because there's nothing more frustrating than opening up somebody else's setup to work with it, and they've got VOPs and wrangles everywhere, and you have no clue what they're doing. So let's just call this VOP set cluster. Now let's use a color node to visualize those values. And we'll set that color. It's going to default to just apply white to all the points. But let's set it to random from attribute and set the attribute to cluster. Now what that will do is for each discrete value in our input, it'll apply some random color to it. So if one corner has a value of 100, that will all get the same color. If this has a value of 200, that will all get another color, and so on. Right now it looks completely random, just due to the frequency of noise that we're using. But if we leave the display on the color and dive back inside the VOP and go to our Voronoi noise, let's turn our frequency down to something like, we'll see, maybe 0.1 could be good for testing. You can see a few very obvious discrete values here. This is one value, this is another, with a couple other clumps in there as well. So it's very important to be able to visualize these things when working with noise. Now, if we execute our Voronoi fracture, it doesn't really look any different than if we just ran the points in directly without any clustering whatsoever. Now, the old version of the Voronoi fracture included these clustering options within that SOP itself, but similarly to the RBD interior detail SOP, the clustering has now been split into a separate SOP. Along the same lines, this means that we can use the same clustering functionality regardless of whether we've done a Voronoi or Boolean or something else entirely. So if we connect the RBD cluster to that Voronoi fracture output, it's not going to be doing anything just yet. Now, I found some of this default behavior to be pretty unintuitive, and you have to watch out for some of these default settings. Like there's this random detach that's turned on, and that means it will randomly detach pieces from the clusters you've defined. And I always want to define the cluster values explicitly with the points rather than doing this sort of random detachment, so I typically turn that off. And I would also set the cluster noise to none, just because if we want to do noise on it, I prefer to add it just to these raw points to begin with. But you'll see that we're still not getting any sort of clear clustering out of this RBD cluster SOP here. And that's partly because the cluster attribute is not being exported from our fracture. So if you go to the Voronoi fracture here and scroll down, you see this option to copy cell point attributes. So we can copy any of the attributes that exist on our input points onto the resulting geometry. In this case, let's copy over that cluster. You can go to this 2-piece points parameter, and in the drop-down you'll find the cluster attribute, and these options are auto-populated from whatever exists on those points. But still, this RBD cluster will not work. Now, yeah, I found this to be some pretty unintuitive behavior, but you actually seem to need to include the constraints into your clustering in order for it to do anything. Now, one of the cool things about the new Voronoi and Boolean fracture nodes is that this second output will give us our constraint geometry. And we'll talk more about constraints later in the class, but essentially these lines define which pieces are connected to others in the fracture. Let's just rename our null to keep our scene clean, call that constraints. And we need to get the cluster data on these constraints as well. By default, we don't see that there. So if we go back to the Voronoi fracture node and go to this 2 constraint points, we can copy over the cluster attribute there as well, which means that these values are now transferred onto these points as well. So middle mouse on that constraints null, and you'll see, sure enough, it's right there. And on this RBD cluster, if you hover over this middle input, you've got that hint at the bottom that says that's for constraint geometry. And if you connect that to our constraint geo and look at the exploded view, sure enough, we finally have some clustering happening. Now this looks like we're getting pretty close. You've got some interesting clusters defined that are much more detailed than just a standard Voronoi chunk would be, but it looks like some of these pieces are not getting clustered at all. Now the way clustering works is that all of the negative values it considers to be non-clustered. So in our attribute VOP here, let's take a look at our points. And if we take a look at the spreadsheet, and we can sort by this cluster value and scroll up and down, you can see, sure enough, there are a whole bunch of negative clusters there. There's a quick fix that we can apply in the attribute VOP. Instead of just exporting this number as is, we can take the absolute value of that. So just start typing in absolute, drop that between the seed and that bind export, like so. And then let's go down and let it rerun the constraints and the RBD clustering. And sure enough, you can see that now we're getting RBD clusters that correctly correspond to these chunks here. Maybe if we reduce that exploded view amount a little bit, we can see how those match these patterns of points. Now these clustered sections that we've created are still not the most interesting shapes, and generally I don't use this Voronoi noise to define cluster values. We've used that for this example because that will quickly give us nice chunks of different integer values, but usually I would maybe layer up different types of noise to create more interesting shapes. But my favorite clustering technique is to use grouping geometry instead of noise values. So I will create some warped deformed spheres that maybe look something like this. Maybe some other spheres here like so. And just by using these kind of interestingly shaped deformed spheres, we can use that to group different sections of points together or sections of geometry together and generate your clusters based on that. And we'll get more into that later when we take a closer look at constraints, but just wanted to point out that, you know, this Voronoi noise isn't sort of the end of art directing those cluster values by any means. There are lots of ways that you can explore generating these clumps of clusters, and I've used various techniques over the years to do it, and highly encourage you to experiment with different ways of generating those patterns yourself. We should also take a look at a couple different ways that this RBD cluster node can work. You'll see this default cluster type is combining pieces. Now, when we fracture our geometry, each piece is given a unique name attribute. So you see we have 4,000 input points, and if you middle mouse on that Voronoi fracture, you can see there's a primitive attribute name, and there it says there are 4,000 unique names. If we right click and look at the spreadsheet for that, and look at our primitive attributes, you can see that we have unique piece numbers on all of these chunks. Now, if we look at the output of our RBD cluster instead, if you middle mouse on there, you'll see now there are only 21 unique names. The number of polygons and points hasn't changed at all. You can see we have 96,000 points, 56,000 polys. It's the same amount of geometry coming out of our RBD clusters. The only thing that's changed from that RBD cluster SOP is that name attribute. So if you look at the spreadsheet for the RBD cluster, you can see our primitive names have been changed, and they are prefixed with cluster, and they have the number that reflects the number of the cluster value that we've created. Now, if you look at the other alternative to combining pieces, there's this option to group constraints, which will not separate our geometry into, explicitly defined groups based on a name attribute. Instead, that will modify our constraint data. Now, I don't want to get ahead of ourselves here because constraints come later after we've set up our initial bullet sim, but just wanted to point that out just in case you're curious about what the difference is here. And yeah, in this case, the combined pieces is similar to the old Voronoi clustering functionality. We can just pack these up into independent chunks, and we will explore the constraint option some more in some of the later sessions.